And that's what we were going to do. That's all the pictures. All right, so on, let me tell you, somebody was asking when I started teaching here, or I started teaching in 95. I've taught 3101 algorithms 20 times, maybe more, 40 times. I don't know. I've been here 30 years. So who knows how many times I've taught it, right? And usually I used to have 5 tests. The first test was on loop invariance, and half the class would get 0. Right? It was just standard. And it was because they just, don't really, I was thinking it's because they don't really believe the steps and they don't try the steps, right? So that's one thing, is you have to believe the steps, right? And then the second thing is that people would panic because they didn't know how to maintain the loop invariant while making progress. All right? So what we're going to do now is we're going to do the easiest possible algorithm whatsoever. And we're going to do it. So don't ignore it, though, because what we're going to do is we're going to show how having the loop invariant helps you build the code which maintains it, right? How to lay out your thoughts so that you can do this. All right? All right, so these are all the things that we have to do, right? So what's our precondition? We have some number, capital I. What's our postcondition? We add up 1 squared, 2 squared, up to capital I squared, right? Easy enough. What's our loop invariant? Anybody want to guess what our loop invariant is? Jump into the middle of the computation. Say you've iterated little I number of times. What do you know? What have you done? Little I is less than the bit capital I. All right, so that's going to be related to the exit condition. And that's always going to be true until we exit, right? But that alone isn't going to get our postcondition, right? We need a loop invariant that says what we know, yeah? Little I is a variable, so what does that mean?
That I is in the loop and it can go on to the next step once, and that part is true.
Yeah, I don't know what you're saying is true or not true. Yeah. Yeah, but you're giving me an action, right? I need a picture. Exactly, right? We got this much work to do. What's an obvious loop invariant? We've done some of it already, right? Why is that? Well, because we're going to do the work in order. And at halfway through the computation, we've done some of it, right? So our loop invariant, right here, our loop invariant is that we add a new object each time. Is that a loop invariant? No, it's an action, right? Don't fight me, because I'll win. All right? All right, what do you want to be true in the middle of the computation? Right? So now we have a little I and a little s is our entire data structure, right? And what's the relationship between little I and little s? Is that we have the sum of the first I terms, right? Everybody got that? Seems like a reasonable loop invariant. All right, and we can add in here that we haven't exited, right? All right, so there's our loop invariant. What's our measure of progress? How are we gonna, What's a measure of progress? It's just a single number to tell you how much work we've done. Give me a single number. Big I? Big I is how much work we need to do. How much have we done? Little I. Little I is how much work we've done, right? We've summed up I terms. Our measure of progress, the number of terms we've added, right? And, right, every iteration, we have to make progress, right? So this is kind of what I'm saying is we're trying to design the code that will make progress and maintain the loop invariant. So don't worry about it all at once. Your measured progress is I. If you want to make progress, what do you have to do? All you have to do is increase I, right? There, we increased it. According to our measure of progress, we made progress, right? All right. When do we exit, right? Well, probably something like that, but I say don't worry about it right now. All right? All right, this is my little picture here, right? The green road is that you're staying on the loop invariant, it's true. And if you're meditating and your mind starts to wander, should you beat yourself? No, you just come back on the path, right? So here, I want to head in the right direction. So I said I equals I plus 1. And what do? I move closer to where I'm going, right? But what's wrong? The loop invariant's false. So now your job is just to do the simplest possible thing to bring you back to the loop invariant, right? Does that make sense? Yeah?
Partial sum, because as stated, a loop invariant is an assertion that must be true.
Yeah.
Summing up numbers at that point, the sum from one side, the sum must be true.
Yeah, exactly. All right, so this will help us determine what we do each iteration, right? That's our goal, is to design the algorithm from the loop invariant, right? My motto is, you're told pre and post condition, jump in the middle, get the loop invariant. Use the loop invariant to design your code, right? So that's what we're doing here. We're designing the code. All right. So, Was it this course? Maybe it was a different course. Somebody gave me markers. You gave me markers. What did I do with the markers? I hid them. Where did I hide them? I don't know where I hid them. Anyway, let's lay out what we're doing here. All right. So here are the things that we know so far, right? Everybody we got what our loop invariant is, what our partial loop is, and what we're trying to do, we're not worrying about establishing the loop yet or the post condition. We're just working on the code to maintain the loop invariant. And why are we doing that one first? It's the harder one. The other two usually aren't so hard, right? All right, everybody see what we're doing? All right, so how do you prove an implies, right? You do it by, remember deduction? You assume the left-hand side, you do some magic, and you prove the right-hand side, right? So how are we going to do, what do we want our final proof to look like? Oh, well, first we need some notation, right? Let IT and ST be the values at the top of the loop, and T plus 1 when you come around again, right? Why do we do this? So that we can talk about these values, right? All right, so this is the big picture, right? We're going to assume that stuff over there, and we need to prove this down here. And what I'm doing in 1090 right now is, you know, a Hilbert proof is you start from the axioms and you keep going forward till you get this, right? Yeah, but you don't have to do it in order. You can also work back some, right? We can keep playing. We want to get from here and then we want to eventually get here, but we'll play in between. All right? All right, first, we want to say from each of these things, what do we know? All right, from our code. All right, what do we need to do? We got to make our loop invariant true, right? How do we do that? Oh, I don't know how to make the loop invariant true. That's hard. How do I solve the entire program, right? I panic. And what do you do when you panic? You drown, right? All right, don't do that. All right, one step at a time. All right, the key is that you don't have to do this all by yourself, right? You have to use the things you already know, right? Hear what I'm saying? You just need to make one step, right? You can't run around and deliver the baton to the next guy until you've actually received it from the person before you, right? All right, so what do? We say, what do we know from all of these? What does that say? That says that the loop invariant is true for the values at the top of the loop, i.e. for the t values, right? So what we do is we just go look at our loop invariant and we copy it down for the t values, right? Everybody see that? I'm just saying the loop invariant is true at the top of the loop for the values at the top of the loop, right? Right. What is the exit condition? It's probably something like this, right? We haven't exited. All right. What's the code? Well, we have that code, right? Is it math? I equals I plus 1, is that math? No, right? So we have to translate it into math, right? Everybody see how this tells me the relationship between the old values and the new values, right? All right, now let's work backwards. What do we need to prove? We need to prove that the loop invariant is true after we go around again, right? i.e. for the t plus 1 values, right? So we just copy it down, right? Here you see I've copied it down, right? Now, the difference between what's up there is those are things that I know, right? And this is what I want to prove is true. I don't know it yet. And now you might think, how do you prove that something equals something, right? You usually say, well, the first something equals this, which equals this, which equals this, which equals to something, right? So you kind of say left-hand side. Have you used this notation, left-hand side, right-hand side, right? We want the left-hand side that we want to be true is this, and the right-hand side is this, and we got to make them equal. So we can work from the left-hand side forward, we can work from the right-hand side backwards, and we can bang them to be equal, right? Now, let's first pause for a moment and think about how much thinking have we done so far, all right? I'm saying you should always lay out, now to be fair here, yeah, no, I'm not, right? You should always lay out your proof like this, right? And then we're just, when I say have we thought so far, I meant we've already come up with the loop invariant, right? So you just copy in the parts that you need, right? We're just laying out the basic structure. And if you were to do this on a test for me, I would say, all right, you know, we're really moving along, right? And what I was just saying, he might know, I just said this morning, if you kind of do this and then there's a magic in between and you just hope the TA doesn't notice, then I feel lied to you. But if you say at this point, oh, I got this far and I'm stuck, right, then I'm impressed that you're honest with me, right? So you could just stop right here and you'd probably get a lot of marks, right? All right, so now let's keep going. We say, well, I gotta make this look like that, right? And so what can I do? I can note that that is the first, all but one term, right? And so I can start comparing what I know, right? So here I take this line and I separate out the last term because that's kind of useful, right? And right. Oh, and you'll note maybe, I think this might be the Reader's Digest versions of the slide, or maybe they were the slides before I've updated them over the years, but there are more slides than 3101. But you'll notice IT plus 1, right? In fact, this line is kind of funny up here, right? You'll note the same characters are happening here, right? But this is IT plus 1, where this is IT plus 1, right? So, and we're doing a little magic of that when we got here, right? Because this is IT plus 1, and then we noted that we would take this and replace it by that, right? So that this is the previous term, right? There was some magic happening in there. Everybody see that magic? And maybe we'll update the slides so that magic is not so hidden. All right. And then I say, now I use the loop invariant, right? By the loop invariant, all this stuff equals ST, right? So I can just plug it in, right? Now, again, why do I have an equal sign here? I haven't proved that yet, right? Everybody see that this thing equals this, which equals this from what we have up there, right? And what is this line here? What's that top equals? What is this equals right here doing to us? How do we get that to be true? Right? What is it saying? It's saying you take ST, which is our old value of S, and you add on what's our next term. And what do you want to get? You want to get the new value of S, right? How do we get that to be true? Who does that? Yeah. Who's going to make this happen? Remember let's step back. What was our goal? We started with the loop invariant. And what are we trying to do? We're trying to develop the code within the loop, right? And do we know the code yet? Right? Oops. We don't know the code yet. We have partial code here, right? This is the code that makes progress, right? Now we need code which will get us back on the path, reestablish the loop invariant, right? And right? So this loop invariant, when you just change I and don't change S, isn't true, right? And how do you make it true? Well, you got to update S, right? And how do you update S to make this true? How do you update S to make this true? Yeah, I mean, you got to do this, right? So we're going to convert that. Right, that's the math statement that we want from our code, right? Our code's going to give the truth, this truth. And you'll see what order. This is now kind of a nice proof, right? But we didn't write it in order. And we started writing the proof before we even, we're trying to prove that our code maintains our loop invariant while making progress. And we started writing the proof before we even knew what our code was going to be, right? We said if we were going to have a proof that our code maintains the loop invariant, what would that proof look like? It would look like this. How much of it can we fill out to be true? Well, up until this equals, right? How do we get that equals? Well, bang, it tells us the relationship between the new values and the old values that we need, right? And hence, we can, right? Everybody good? All right, now we need step. All right, is this good code? How many people are liking this code? How many people are not liking this code? All right, watch him. He gives the right answers, all right? It's not good code, right? Why is it not good code? It's because what we're supposed to be adding onto S is the new value of I, right? And here we're adding on the old value of I, right? And in some ways, you know how you write code and your code is always off by 1, right? And it's because you haven't been clear about what your loop invariant is. And the loop invariant here says, I'm done up to I. So what's the next thing to add on? I plus 1 is the next thing to add on, right? So don't add on I because we already have it added on, right? So that works, right? We get a new value of I, and then we add in our new value of I. Yeah? What do you think, guys? All right, now, on one side, I might argue that what I'm teaching you here is more material. We were supposed to cover loop invariants, right? But we're doing a little bit more, I think. And I really do think that it will help us when we're writing code. All right? Everybody kind of follow how we're doing this? And you see it was a really easy example, but it kind of showed you what we were doing, right? Okay. How are we doing for time and everything? We got 15 minutes, lots of time. All right. All right. So now, finish this example. We got to get the post condition, right? So again, right, on the test, it might say, prove that we're maintaining the post, we get the post condition, right? So you write down what we have, right? We have the loop invariant Y because we maintained it. We have the exit condition is true because we've exited. And we got the code in the loop. Why? Because we executed it. And we got to get the post condition. Oh, this is not the code in the loop. That's the code after the loop, right? Let me give you a little hint about this whole process that I just thought of, all right? The midterm that you're writing is written by me. The exam you're writing, except for extra little bits, are written by us collectively. So things like this, I should slip into the midterm because they might not make it to the exam. All right? All right, everybody good? This is what we want to do? right? So how do we do it? We bang out. What do we know about the loop invariant? There we have the loop invariant, right? And why didn't I use t values this time? Remember before I said I plugged in I sub t and t plus 1. And I'm not doing that now because, yeah,
That's what the both conditions of that.
yeah, it's because we're not, in this little block, we're not going to be changing the value of I, right? So I is the value at the top of the loop, I is the value until, all right, what do we, the exit condition, right? So, so it just kind of follows, right? Everybody sort of see what we're doing here? Again, my 3101 slides are longer than this, but maybe you don't even need longer, right? We need to get the, in fact, we could have, in the 3101 slides, it helps us design the exit condition, right? I need this, I have that. How do I make them the same? I got to make little I, capital I. How do I get that to happen? My exit condition, right? I also have to make little s, capital S, right? How do I do that? Well, I do it the other way around. I set the value of capital S to be little s, right? And then we got what we need, right? Does that make sense? Right? I'm trying to turn the loop invariant into the into the post condition. And the things I have at my disposal are the exit condition and the code at the end. Right? Does that make sense? All right. How do you establish the loop invariant? Right? You can do some examples here. Right? What's the value of S when I is 0? 0, right? So there we go. Everybody good?